Alrighty, let's have a look-sees at what we've got. Ooh. Alrighty, hello everyone, if anyone is joining. Welcome to my little go at this exam here. So yeah, we got stuck into it. Felt like doing a little bit of live streaming of an exam paper, and you know, here we are. I'll preface this now by saying that I'm probably not going to get all of this right, despite teaching the subject, but we'll give it a crack and see how well I go. Alrighty, so they reckon 3 hours, that'd be 10 o'clock. If we can try and knock it over in 2, I'd be pretty happy. Yeah. Alrighty, start with multiple choice, nice and easy. So, which inequality gives a domain? So, in this case, domain is just essentially what can exist. So, I think, not think, but basically anything inside a square root can't be negative, or in other words, it has to be greater than or equal to 0. So it can be 0 because the square root of 0 is 0, and the square root of any positive number returns a well, something. So but the negatives don't work. So solving this inequality, we get 2x is greater than or equal to 3. So x is greater than or equal to 3 and 2, and so it's this one here, D. Alrighty. Next up, we've got this guy here. So the function f of x is equal to x cubed is transformed by this. So quite quickly, translations. So you've got 2 different types of transformations. And it is your translation or your dilations. So translations, horizontal or vertical. Your horizontal dilations, you're just replacing the x value. Hang on, let me think about this. Yeah, you're replacing your x value with x minus however many you want to go. And your vertical translations, you're replacing y with y minus how much up you want to go. So, for example, if you wanted to move it 2 up, you would replace the a, or you'd replace y with y minus 2. So for the 2 up. Your dilations, let your x becomes x over a for your horizontal, and your y becomes y over a for your vertical. So in this case, we've only got 2 applications of this. In fact, it actually tells us what they are. So 2 units, 5 units. So in this case, we're replacing x with x minus 2, so it's going to be 2 to the right. Okay, so it's either that one or that one, and your plus 5 on the end. So originally, if we move it back to the other side, it's g of x minus 5, or, you know, if we call our function some form of y, so to graph it per se, that's just y minus 5. So in fact, it's going to be a translation of 5 units up, or if you can see that's there, the plus 5 on the end is essentially saying, let's just take this function over here and shift it up 5 spots. So it's going to be this guy over here. Okay, so John recently did a class test in each of 3 subjects. The class scores on each test were normally distributed. The table shows the subjects and John's scores, as well as the mean and standard deviation of the class scores on each test. So your standard deviation is essentially telling you what the spread is. Each value of the standard deviation is, you know, obviously further and further away from the spread. So in this case, for French, the mean was 70, and his score was 82, so it's quite more than the rest of the class. Commerce, he again scored a lot better, and music he scored better than the average too, so quite a bright boy in this regards. Now, relative to the rest of the class, which row the table best shows John's strongest subject and his weakest subject. So let's take a look at commerce, because I think that's the easiest one to see. And just from looking at it, I can see that's going to be the biggest one. Basically, to work out whether or not he's doing better, it's just how many more standard deviations is he above the mean. So from 60 to 65, then 65 to 70, then 70 to 75, and then from 75 to 80. So by doing jumps of 5, we can see how many standard deviations he is above his class. Well, in fact, actually, we don't start at 60, we start at 65. Anyway, so we can see that he's, 3 standard deviations above, so plus 3 in this case. This one here, 70 to 78, and then 78 to 84. So 82 is halfway between, that should be 86 anyway, shouldn't it? Yeah, not 84. 82 is halfway between those two values, so it's going to be, 1.5. So 1.5 standard deviation. So you can see in this case, even though it's his best score, compared to the rest of the class, he's only 1.5 standard deviation. So, the spread of everyone was quite wide. Whereas in the regard of the commerce, the spread wasn't as much, but he performed much better in that case. And this one here, so we're going by 12, so from 50 to 62, and then to 74, so that one's our plus 2. So that means our commerce is our strongest, so one of these two, and the weakest one is the French, so that gives us A. Okay, classic integral. So what is the integral of e plus e to the 3x dx? So essentially asking ourselves, what did we need to differentiate to get to these functions here? Okay, so if I differentiate e, okay, well, there's no x term in that, so it's just going to give us e to the x. Integrate that, I should say, not differentiate. E to the 3x, so think about what we would have needed to differentiate to get there. So if I differentiated e to the 3x, then I would get 3e to the 3x. So the derivative of the inside comes down the front. But we want to end up at e to the 3x. So we don't want this 3 here. So the easiest way to do it is to essentially divide by what our derivative in that top is. So in this case, our derivative of that, so our derivative of 3x is equal to 3. So 1 over 3, so divide by that derivative, e to 3x. So which one does that give us? Well, can't forget the constant term. So including the constant term, e dx, and then the third e to the 3x must be b. Okay, which of the following could represent the graph of y is equal to minus x squared plus bx plus 1? Okay, so first things first, look at the y-intercepts. 1, 1, 1, 1. Well, that hasn't really helped us. But we can look at this bit next, which is the negative in front. So the negative in front is telling us that it's going to be a concave down parabola, so that knocks out A, and that knocks out B. So we're left with these two. So the question now is it a parabola that's been translated to the right, or is it a parabola that's been translated to the left? So we've been told this key piece of information about the parabola, that b is greater than 0. So for example, like say 2. So what we could do is we could actually, put a positive number and replace that, and actually try a positive value. So let's say we try 1, for example. Okay. Now, what we're hoping for is a number that's actually bigger than 1, because if we have a look on this side, all these values on the positive side of the x-axis, or the y-axis I should say, well, no x-axis, the positive side of the x-axis, we've got values of, that should be below the 1, whereas on this side, we've actually got some values that are greater than 1. So if we just try the next value up, like really, really close to the 0, but not exactly, but close, we should be able to see something resembles it. So minus x squared, so let's try 0.01, because realistically, if it should give us something that's bigger, okay, or smaller, depending on what it is. So look at this, it's bigger than 1, so it must be this c value here, nice and easy. Okay, which interval gives the range of the function y is equal to 5 plus 2 cos 3 of x? Well, let's start off by looking at the function of cos of 2x, something like that. Probably not as poorly drawn, but something like this, okay? And the cool thing about cos is it goes from from -1, why have I got something like that? So +1 to -1, okay? Jeez, must just be the first stream nerves. So looking at that there, we can now apply the transformations of this function. So this +5 at the front here is actually shifting our function up some amount. In fact, it's shifting it up 5 spots. So if we add 5 to each of these, okay, we should be pushing this thing up, and our new range becomes 6, and it becomes 4, so 6 and 4. Now, the 3x on the inside is basically reducing the period that this this function is going across. So what it's basically saying is for every normal, so for every one of these, sorry, 2π, for every one of these, you know, periods we've got, we could actually fit 3 of the periods instead. So that's not actually going to affect the range whatsoever, but this number at the front, this +2, or this 2, is basically saying take your function and double it. So all the values, all the outputs are going to get doubled. So, I'm suspecting I've done it in the wrong order, because that's none of the answers that I got. If we have a look at that again. So instead of translating it first, so as I said, so the period doesn't affect it whatsoever. So if we go from +1 to -1, this 2 is going to double that, so it's going to go from 2 to -2, and then adding 5 now, so +5 is going to push it up to 7, and push it up to 3, and that looks a lot better. So just be careful with your with the order you do transformation. Start from the inside, work out. I think that's the takeaway message from this. Okay, diagram shows a graph of f of x, which is made up of line segments and semicircle. So we need to find an integral of that. Now, unfortunately, I don't know what the integral of that is, but fortunately, we can use the fact that the integral of a function is very, very, very similar to the well, it's essentially the area under the curve. So basically, if we break this curve up into parts and calculate the areas of that. So if we have a look, we've got a 3x4, a 3x4, so 3x4, a 3x4. We've got a semicircle up here, okay, and we've got some triangles. So a triangle here, and a triangle here. So it's 3x2, and this one is 2x3. Now we just need to keep in mind this area down here is going to produce well, it's going to be a positive area, but for the case of the integral, it's going to give us a negative value because we want the difference between the x, or the curve and the x, or the x and the curve, depending on which way we're going. So let's have a look at this bit first. Well, actually, we'll look at that bit last because, you know, it's quite an easy bit. So 3 times 4 is 12, 3 times 4 is 12. We've got 3 times 2, which is 6, and half of that is 3. So I might put that on the inside, and then the same for this one down here as well. So 3 times 2 times a half for the area of a triangle, and that just gives us 3. Okay, now we just need the area of the circle. So it's a semicircle, so it's a half times pi times the radius squared. So the radius is 2, so 2 squared. That's going to cancel with that. We're left with 2 pi. So now total area, or we should say, in fact, total signed area, because the signed area is essentially what we're going to be calculating. So it's going to be the 12 plus the 12 plus the 2 pi plus the 3 minus the 3. So that guy's going to disappear. I'm going to be left with 24 plus 2 pi. So you can see where that has come from, and you can see where the 30 comes from as well. If you add on this as a positive area, so if you were asked to calculate the area, then yes, you would add it on because it's an area. You can have a negative area, and it adds to the total area. But because we're just asked to find the value of the integral between 0 to 12, it has to be taken off because the integral is the signed area under the curve. So because it's in the negative zone, it's treated like a quote-unquote negative area, and then from there we can actually we can calculate it. Okay, let's have a look at number 8. The graph of y is equal to f of x is shown. Which of the following inequalities is correct? So we've got the second derivative at 1 is less than 0, which is less than the first derivative at 1, which is less than the function's value at 1. The second derivative at 1 is less than 0, which is less than the function value at 1, which is less than the derivative at 1. And then we've got the other two underneath, where we've got 0, or that the second derivative is bigger than 0, but less than the first derivative, and less than the function value at 1, and where 0 is less than... Sorry, the function... second derivative at 1 is greater than 0, but less than the function value at 1, which is less than the derivative at 1. So, after getting that mouthful out of the way, let's have a look at the possible values, or the possible things about this. So, just looking, so in multiple choice wise, looking at this bit here, we could probably get rid of 2 of our answers straight away. Either the second derivative is going to be bigger than 0, or it's going to be less than 0. So let's work out what that's going to be. So it's a concave down function, okay? So essentially, if you think of the cave is pointing to the south. So because the cave is pointing to the south, that essentially is saying that the second derivative is going to be less than 0. Okay. So what we can do is we can cross out C and we can cross out D, and that leaves us with A and B. Now we need to work out, well, is the first derivative less than the function value, or is the function value less than the first derivative? So looking at this function, what can we say about it? The function itself is growing, so the derivative is getting higher and higher and higher the further we go up the function. But if we were to take a value at that function, or at any point, we would notice that the function value is actually decreasing, so it's going down. So what we would state then is that because it's increasing at a decreasing rate, okay, so it's going up, but it's going up slowly, okay, then we would have to say that the function value must be bigger than the derivative, okay? I hope. Anyway, I'm going to lock that in, and I'm going to check that one a bit later on. Because, yeah, well, it actually depends on whereabouts you would find that value. Anyway, that's what I'm going to lock in, and I'm going to check that one later on. Because, like, if you had it down here, say, like, that's a pretty steep gradient there, but the value at the x value is not very high. And then whereas here it's not, like, that's a bit odd. Oh, well, I'm going to ignore that, and I'm going to go back and check that later on. I think that's what it is, but I'm not 100%. Okay, what have we got? Suppose the weight of melons is normally distributed with a mean of mu and a standard deviation of sigma. A melon has a weight lower than the quartile distribution, but not in the bottom 10% of distribution. So a melon has a weight below the lower quartile and not in the bottom 10% distribution. Now, the statistics stuff I haven't, and probability distributions and stuff I haven't really touched on yet, but we'll have a look and see what we can try and work out from here. So that's the average and standard deviation. So each of these is a standard deviation underneath the, or from the mean. Okay. Okay, so which of these does not accurately represent the area or the region in which the weight of this melon lies? So it's below the lower quartile. So the lower quartile, so if we split these up into 4 bits, we've got, you know, so that's our, so if you think this is as your middle, this is as quartile 1, this is a quarter 3, okay, and you go from there. So from that description, so our Q1s, everything except for B, so if we look at B here, that's where our quarter is, but we've got some area out over in the positive value of that. So it's not going to be B in this case, and it neither is going to be C as well for the same reason. So we can knock those two out. So that's taking care of the lower quartile, but not in the bottom 10%. So if it's not in the bottom 10%, if we go back to our rules about, what do you call it? The rules on, so I think it's called the 68, 95, and 99.7 rule, which is, you know, 68% of your data lies in this area, 95% lies in the next segment, so between, you know, here and here, you've got 95% of your data, and then if you extend this out to the third standard deviation, then you have got this bit too. So if we're not including that bottom 10%, well, that's going to pretty much void this little bit here, because that's our extra bit on top of that. So my hunch is to go with D, but as I said, I haven't actually done this yet, not in much depth, but just from my background knowledge in statistics, which is not a lot, I actually suspect that's what it might be. Anyway, let's move on. The graph shows two functions. Okay, those are two functions. I'm going to define h of x as the... Okay, so it's the... what's the word? It's the function of a function, f of g of x. So essentially what it's saying is take the values at g of x and put them into f of x. Okay, so... And then whatever you put in, you're going to get out. So... Ooh, this is... Okay, I've got to think back to this one a bit. So, h of x is equal to f of g of x. How many stationary points does... So, looking at this... f of g of x. So, the x values I put in, they give me the g of x out in return. I'm taking the g of x results out. So, I'm taking what the outputs are of the g of x and putting them into the f of x. So... Okay, so I think how it works is, so if I go f or x, f of x, actually other way around. So if I go x, g of x, and f of x, okay. So looking at these, my x values, so 0, 1, 2, well actually I don't even need 0, but 3, 4, 5. Okay, we'll start at 1, so if I put 1 into g of x, I get the value of... It's about 2 back out. Okay, so I get 2 back out, and then I put 2 into f of x. So I put 2 into f of x, and I get 1.5. Okay, so 1.5. So the value I get at 1 is 1.5. So, and I might use a different color for that one, so I might use blue. So that's my first point there. Okay, I take 2 and I put it into g of x. So 2 into g of x is here, which is about a half. So I get 1.5. I take a half and I put it into f of x. So half into f of x. And that just gives me about 2. So my next point is at about here. Alright, put 3 into this. So if I put 3 into g of x, we get 0. So I put 0 into this guy, and I get about 1.5. So my point's going to go... So 1.5? 1.5? A bit higher than that. About there. Okay, we can kind of see already that we've got this sort of thing happening like that. So there must be a stationary point. For it to go up and then to go back down, it must stop at that point, at somewhere between it, unless it's not a function. But we know they're both functions, so it's going to. So it's about 2, roughly 2. Okay, let's take 4 and we'll put it into g of x. So that's about a half again. So 1.5. Oh, sorry, 0.5. In fact, it actually should be pretty symmetrical from this point because it is a parabola. So we put 0.5 in and we get, well, that's just going to return us with 2 and that's just going to return us with 1.5. So 4 gives us 2, 5 gives us 1.5, like that. So it's going to look like that. So the amount of stationary points we actually have is, so that's flat, and that's flat. We've actually got 3 stationary points. So that's quite a few, actually, which is crazy. Cool. All right. Oops. All right, and that concludes the multiple choice section. So it took half an hour. I think I was given what? How long was I given to do multi-choice? Oh, about 15 minutes. So I only took double the time. All right. Well, let's see how we go with this next bit. Center number. The best number. 1. Student number. 3, 4, 2, 0, 0, 6, 9. That's my number right there. Classic number. I don't even know what that is. I just made it up. Anyway, enough of the giggles. Let's do the next bit. So there are 2 tanks on the property, tank A and tank B. Initially, tank A holds 1,000 liters of water and tank B is empty. So, well, we can, I'm guessing we have to plot these, so we can do that straight up. So initially, A has 1,000, so A is up here. And the other one is initially empty, so we can put that point there. So initially just basically means when the time is 0. So constant rate, in fact I'll do it like this, so a constant rate of 20 liters per minute. So that is for every minute that it elapses, we lose 20 liters. So if we're going across by 5s, then it's going to lose, so 20, 40, 60, 80, 100. So we're going to end up with this linear function that looks like this. I'm going to grab the classic ruler out. I'm hoping that's telling me that, okay, there we go. So we've got the ruler out and we get this guy looking like this. So that's our first function. And our second function, so the volume of the water tank A is modeled by V is equal to, oh, well, I just did that, where V is the volume in liters and T is the time in minutes where the tank loses water. On the grid below, draw the graph that models this and label it as tank A. Okay, well, tank A, okay. So looking at that graph too, V is equal to 1,000 minus 20T. Y-intercept, gradient. Okay. Okay, so from there, it continues on the next page. Tank B remains empty until T is equal to 15. So at T is equal to 15, it starts to grow when water is added at a constant rate of 30 liters per minute. So constant rate of 30 liters per minute. By drawing a line in the grid in previous page or otherwise, find the value of T when the two tanks contain the same volume of water. So this is essentially a simultaneous equations question, okay, dressed up as a graphing question. So every 5 minutes occur. If it's every 1 minute is 30 liters for tank B, then our every 5 minutes that occur, then we're going to have, 30, 60, 90, 120, 150. So it's actually going to grow up something like this. Okay. So we'll take our ruler. I don't know how to spin this. Oh, there we go. So if we take our ruler, good old ruler, it's going to be a bit higher this time. It's going to be something like... That's looking pretty spicy if you ask me. This guy is going to grow up like this. Okay, and this is our tank B. Okay, so you're essentially looking for where they intersect. So the point of intersection. So this is going to tell us when these things, well, at what time this thing are going to what time they're going to elapse each other, and at how many liters it is. So find the value of T when the two, so T is equal to, what was it, 20, what did I say, 24? 29. Okay, so 29. So you're basically just looking for where they cross over and then down on the time scale. Okay, now if you wanted to solve those simultaneously, which is the other method, it's probably going to give you a more precise answer. So to do that though, setting up the first equation, well, they tell you what it is. It's 1,000 minus 20T. But the second equation is actually a little bit different. The second equation is going to be, so we know it's growing at 30T, but, or every 30 seconds it's going up. But the problem is that it doesn't start at 0, because it's after 15 minutes that it occurs. So if we were to have, or to be able to have a negative part of this question, it doesn't make sense to, but if we were to extend this down here, 150, 150, 150, would actually end up at minus 450. And so from there, we can put that into this bit here, and then we could solve these two equations simultaneously. So because these are both equal to V, I can make them equivalent to each other. So 1,000 minus 20T is equal to 30T minus 450. Okay, from here, we would add 20T to both sides, so plus 20T plus 20T, and we get 1,000 is equal to 50T minus 450. Add 450 to both sides to get 450 is equal to 50T, and then divide by 50, and we get T is equal to whatever that is. I suspect it's going to be 29, and in fact it is, so look at that. So my graph was very accurate, which helps. Okay, so the more accurate graph, so make sure you take your ruler into the HSC. But the more accurate your ruler and the more accurate your drawings, the better you're going to be able to find it. But if you can't draw the picture or you're not very accurate, then you can solve these simultaneously as well. Using graphs or otherwise, find when the value of T, where T is equal to 0, when the total volume of the water in the two tanks is 1,000 liters. So in other words, for what value of T is both of the volumes equal to 1,000? So when are they equal to 1,000 each? When is the total equal to 1,000? So looking at the graph, So 1,000. So we're looking at all the different values. We've got a 600. About 500 here and 300 here. No. 600 here. Not there. It's going to be, in fact, actually, what's that? 900 and 100 here. So at 45 minutes, I think. I suspect. Anyway, the way that we would actually work that out is you would, because there's going to be some point where they cross over. Okay, so we want to know when they're both equal to 1,000. So once we've put the two equations together, so like in this line essentially here, okay. Oh, in fact, sorry, let me rephrase that. No, actually, it's just going to be when they're both equal to 1,000, isn't it? So, so when the first one is equal to 1,000, and so adding it to get to the second one. So it's essentially just when the sum of the two is equal to 1,000. So just equate the equation. So 1,000 is equal to 1,000 minus 20t plus 30t is just 10t minus 450. So that's going to give us 550 plus 10t. 450 is equal to 10t. Divide both sides by 10. And you actually get the 45 is equal to t. So there you go. And again, if we look up to where that value is, so 45 up this line here and down here, it's basically adding that number there to that number there. Okay, calculate the sum of the arithmetic series. Now, the cool thing about the arithmetic series and all the series is that on your formula sheet, you actually get what the sum of the arithmetic or the arithmetic or the geometric sequences and series. So, to calculate the sum, okay, we're going to use the formula. It's going to be the sum of the numbers. It's going to be equal to, and then you can use any one of these. So these are both on your form. Well, I'll just do one of them, but you've got two of these on your formula sheet. It's A, and it's going to be Rn minus 1 over R minus 1. Now, the other one is just with the Rn minus 1 switched around, so it's 1 minus Rn, and the bottom line as well, so 1 minus R as well. So what we need is we need an A value, and we need an R value. Now, our A value is the value that we start at, in this case it's 4, and our R value is, it's an arithmetic, I've written down the geometric one, silly boy. Arithmetic, it's even easier, it's just n over 2, 2a plus n minus 1 d, or alternatively it's equal to the number of the scores you've got, or in your sequence of a first one plus the last one. So it's just basically average. I'm having a bit of a mind blank. So to do this, you'd actually need to know what how many numbers there are in this sequence, which is, just looking over here, I'm trying to work it out. I might actually come back to that one, I think. No point sitting here wasting my time. Come back to that one and I'll do something like this, which I probably can do a bit better. Not too great with my trig stuff, but you can only get better. That's the point. sec squared. Okay. So on your formula sheet, okay, another thing from your formula sheet, this guy here is one of your standard integrals. So your standard integral is, for this particular one, is if you have the derivative on the outside of sec of your derivative, of your function on the inside, then this turns into tan of the function plus c. Now in this case, because we've got a definite integral, we don't need that. So essentially we need to look at our function. Okay, so our function in this case, our u is equal to x, and du dx is equal to 1. So we've got that because there's technically a 1 out there, and so we've got the exact form that we need. So from 0 to pi on 4 of sec squared x dx, that becomes tan of x from 0 to pi on 4. Okay. Now, what we need to do is we need to work out what the values are going to be at those specific points. So again, on your formula sheet, on your reference sheet, you've got the trigonometric functions, and you essentially can just use the exact triangles that they've got on there to work these ones out. Keeping in mind that the tan of 0 and tan of 90, or tan of 0 and tan of pi on 2 aren't on there. So you just got to remember which one is which. So just remembering which one is which right now. So tan is the opposite on adjacent function, so that would equate to having sine on cosine. Now, sine of, so it's when cosine can't equal to 0, which is pi on 2, so that's not an issue there. So substituting these values in, then we get tan of pi on 4 minus tan of 0. Okay, might just double check that 0, 1, because I'm just not 100% confident. Yeah, okay, 0, it's fine. Okay, so pi on 4 is the same as 45 degrees, but thankfully you've got, well, okay, yeah, you don't have both of them, but 45 degrees is the same as tan. So tan, well, that's just 1 minus 0, which is equal to 1. Oh, that's boring. What a long and arduous question to just give you the answer of 1. But I mean, you know, that's some mathematicians are about that. Anyway, so history and geography are two of the subjects students may decide to study. For a group of 40 students, the following is known. Seven students study neither history nor geography. 20 students study history, and 18 students study geography. A student is shown at random. By using a Venn diagram or otherwise, find the probability that the student studies both history and geography. So a Venn diagram, one of these circle boys. Okay. So we know that there are 7 in this group at all. So there's 40 in total, and 7 of them aren't in there. So we should have 33 kids in some combination of these. Okay. So we know that 20 students study history and know that 18 students study geography. Now, if you are one of the astute amongst yourselves, you may notice that 20 plus 18 does not equal 33. In fact, 20 plus 18 equals 38, which is a bit of an issue. Now, this is where the fun part comes in. We know that there are 20 kids that study history, and we know that there are 18 kids that study geography. So I'll do this in a two-way table, actually. I think a two-way table is a bit nicer for this one. So you've got history and not history, and you've got geography and not geography. Okay, and your totals there. So we've got 40 here, we've got 7 here. Now we know that our total for non-geography is going to be 18 students. So that means that 11 of the students, geography's over here. So 18 students study geography, so we can't touch that one just yet. We know that 20 students study history in total. It means that there's 20 students that don't study history at all, and it also means that there are 22 students that don't study geography at all. Now, from this, we can work out our different values. So we know that 13 don't study history, but do study geography, which means that 5 study history and geography, which means that 15 study history and not geography. And filling in this guy, what's this guy called? The Venn diagram from across this, we'll notice that all 40 of the students fit into that. Now the actual question says, find the probability that student studies both history and geography. Well, that's the probability of history intersection geography, which is 5 out of the total 40. So yeah. So really straightforward once we get to that. Now, a student is chosen at random. Given that the student studies geography, what is the probability that the student does not study history? So given that the student studies geography, so they're told that they must study geography. So if I label my guys up here, so this one's more useful, I think, the Venn diagram is more useful for a question like this one. I just find it easier to visualize. So here's my history bubble, okay? So that's my history bubble there. Now, out of my history bubble, my geography bubble. That's my geography bubble. So those are all the people that study geography. So given that I've picked someone and I know that they study geography, how many people is that in total? Well, that's 20 people in total. Now, out of that 20 people in total, what's the probability that one of them studies history? Well, there's 5 people who overlap in the history bubble. So it's going to be 5 out of the 20 in the geography bubble, in the total geography bubble, or a quarter. So I've got a quarter chance of picking someone who will do history if I know that they do geography. I also cannot seem to add numbers up. Chances are a bit easier. Out of 18, not out of 20. Now, 2 different students are chosen at random, one after the other. What is the probability that the first student studies history and the second student does not study history? So the probability that the first kid, so out of a total of 40 kids, the chances they study history are 20 out of 40. Times, now it's times because it's a new event, the probability of a kid. So now we've only got 39, because if I'm picking 2 kids, okay, unless it told me that they went and sat back down, which it hasn't, I'm picking 2 kids, 39 now, and I want that they do not study history. So looking at this, that's either this number here or that number there. So it's also going to be 20 out of 39, okay? So you put that into your calculator. Now, thankfully in the HSC, we're a bit more convenient, well, not convenient, but my understanding is if you just put the calculation in, well, I knew that. If we put the calculation in, the calculation that you would do onto your paper, you should get full marks. But I would not take that bet. I would make sure that you put the answer as well. But just in case you forget your calculator for the your biggest exam that you've ever done. So 10 out of 39 is the answer, by the way. Actually, that was quite an easy fraction to solve. Anyway. Yeah. Anyway. Mr. Ali, Miss Brown, and a group of students were camping at a site located at P. So that's this point here. Mr. Ali walked with some students on a bearing of 35 degrees. To location A. So on a bearing of 35 degrees means from north, 35 degrees around like that. Miss Brown and the rest of the students walked on a bearing of 100 degrees for 9 kilometers. So that's 100 kilometers from there to there. Or this little bit here, which we can work out straight up, is 65 degrees. Show that the angle AB is 65 degrees. Well, it helps if you write the question. 100 degrees for him, minus the 30, sorry, for her, minus 35 degrees for him, gives us the 65 degrees for there. Another way to write that out would be to write something like APB, so angle APB is equal to angle, angle BPN minus angle APN. Okay, so something like that first, but I would suspect that this calculation would be fine. Find distance AB. So we've got a non-right angle triangle here. So if I connect these up, this is my length AB. Okay, I need to find that distance there. So looking at this, I've got a side. Oh, that was pretty horrendous. I've got a side. I've got a side. I've got a third side. So as soon as I'm looking at a third side, I'm going to be looking at the cosine rule. Okay, so cosine rule is when you're usually involving a third side to your problem. So finding an angle given three sides or finding a third side of a triangle. Your sine rule is usually when you're doing 2 and 2. So, you know, 2 angles and one side and finding one side. So 2 and 2, or 2 angles, 2 sides and finding an angle, finding an angle. Anyway, let's move on and find the distance. So the distance, so c squared is equal to a squared plus b squared minus 2ab cos c. Don't ask me why I remember that. It's just one of those things that stick in my head. So my c is this distance along here. We'll call it ab. So ab squared is equal to. So let's call this side a and this side b. Okay. 7 squared plus 9 squared minus 2 times 7 times 9 times cos of 65 degrees, because that's our included angle, is the 65 there. That's why they asked us, and in fact, if you didn't know how to show that this angle was 65, it's telling you that it is. So if you didn't do part A, you should still be able to do part B, because it's telling you what the value should have been. Okay, so from here, we can take the square root of that atrocious sum. So 7 squared plus 9 squared minus 2 times 7 times 9 times... you could get the value of here and then do the square root, but I like to do the... I like to get it as close as or accurately as I can. So... it's going to go square root 7 squared plus 9 squared minus 2 times 7 times 9... My little laptop, my tablet's being a little bit annoying at the moment. Just keeps disconnecting and reconnecting. Hopefully it'll fix itself before I use it next. But cos 65 degrees, pop that in, we get 8.76. There we go. So 8.76 to 2 decimal places, we'll say. 876. And find a bearing of Mrs. Brown's group from Mr. Ali's group. From Mr. Ali's group. So let's get rid of some of this stuff that's on here. Okay, so we're going from Mr. Ali's group. So that means if we were to draw a set of bearings here. So from Mr. Ali's group, we're going to be going down this direction till we get to this line there. Okay. Because we're going from his group, that means we're going to her group, so we're going in that direction. So it's going to be 90 degrees plus something. It's going to be plus whatever this angle is in here. Now, there's a handful of ways that we could actually do this. I'm just trying to think of the way that would probably be a bit easier. Okay, so if we have a look at this angle in here, so we know that this angle all the way down here is 100 degrees. That means that this angle in here must be 80 degrees there, okay? If that angle in there is 80 degrees, what we've got is we've got something that we call alternate angles, okay? And the alternate angles state that in here we must have 80 degrees. Now, why I've said that, I've got no idea, because I don't think that actually helps us. But, get rid of some of this crap that's on here. So we've got this guy going down here, okay. We know that it's 90 degrees from there to there. Okay, we know that it's 65 degrees in here. I'm saying we could possibly find that angle in there, but that's not going to help us with the bearing. That's really tough, actually. It's actually making me think for a bit. Doesn't help that I haven't done trig in ages. But hey, you know, can't memorize everything. I mean, you have to for your exam, but it's not always the best thing. I guess this is the part where I'd be open for suggestions, but I just can't think. Probably doesn't help that it's 8 o'clock at night and I'm trying to do maths. Who does that to themselves? Jeez, I think there's a bit of work in this actually. So that's 80 degrees. Which means that that's 80 degrees from there to there. So the north bit. Means that we've got 100 degrees in here. Means we've got 100 degrees in here. So is it 10 degrees? So, no, that can't be right. No, because it's this line here, isn't it? So it's not that that's 80 degrees, it's this whole bit in here that's 80. So there's 100, so bang, 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 bang. So that is 100 there. Which does make that 80 degrees, doesn't it? It'd have to be 80 degrees. So if that's 80 degrees there, then bang, bang, bang. So this one just doesn't feel right. I'm gonna come back to that, I think, because that just feels wrong. So I'm gonna write down 10 degrees is my guess. Oh well, it'd be what, 100 degrees. But I'm gonna check this one because I'm not actually sure how to do it. All right. Okay. Let's move on. Okay, sketch the graph. Oh, I can sketch graphs. That's not an issue. Labeling all stationary points and points of inflection do not determine the x-intercepts of the curve. I like when they say not to do the, I need to get better at my lines. So because it's only a sketch, we only have to do like a quick little drawing, which is good. But we do need to label where all the stationary points are. Okay. And it does say points too, so we're gonna have to work out the x and the y values. Do I have some space to draw this thing, or is it just the lines? It's just the lines. Okay. So sketch the graph of the curve, labeling the stationary points and the points of inflection. Do not determine the x-intercepts of the curve. Okay, so well, let's look for the stationary points. So if y is equal to minus x cubed plus 3x squared minus 1, okay? So stationary points occur when the derivative in respect to x is equal to 0. So in other words, when this guy is equal to 0. Okay, so if we factorize this, we get 0 is equal to x. Well, it's actually going to be 3x, lots of, 2 minus x. So therefore, stationary points are at x is equal to 0 and at x is equal to 2. And that should make sense too, because if you think about a cubic, which is what this thing is, like it goes up, down, and up, there should only be 2 stationary points. That should also mean there should only be 1 point of inflection too. So what we'll do is we'll get what these stationary points are. So at x is equal to 0, we get y is equal to minus 0 cubed plus 3 lots of 0 squared minus 1. So y is equal to minus 1. And therefore, the stationary point is 0 minus 1. And at x is equal to 1, 2. We get y is equal to minus 2 cubed plus 3. Now, the reason I'm substituting these into the original equation opposed to the derivative is because we're looking for the specific points that this thing lies on the function itself. So not on the derivative function, but on the function itself. So this is going to be minus 8 plus, 4 times 3, which is 12, minus 1. So y is equal to 3. So therefore my stationary point is 2, 3. Okay, so if I go back up here and put those on there. So 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. Something like that. Okay, so the stationary points are, so it's 0, negative 1. So one of my points is going to be down here. And my other point is going to be, 2, 3. So at 2 up to 3. So it's quite easy to tell what those 2 stationary points are. So we're going to have a minimum and we're going to have a maximum, okay? Because they're going to go to that point and go to that point. And because we know the stationary points, it has to stop there and it has to... Well, I suppose it could actually keep going. So what we might do... Well, we know it doesn't because it's only a single root. But we might... We'll check the stationary point... the type of stationary points they are. Or their nature. So to check the nature... And for the points of inflection, we just have to use this. We'll use this as well. So the second derivative in this case is going to be minus 6x plus 6. So at x is equal to 0, we've got my second derivative equal to minus 6, so therefore it is a, now I'm going to get this right, it's a minimum, okay, because the cave is pointing up. And at x is equal to 2 my second derivative is equal to, what would this be equal to? This would be equal to, so minus 612 plus 6, which is minus 6, so therefore it's a maximum. Now for points of inflection, so more points of inflection is when my second derivative with respect to x is equal to 0. Or in other words, when minus 6x plus 6 is equal to 0. Okay, so just solving this equation, we get minus 6x is equal to minus 6, x is equal to 1. Okay, and point of inflection. So y value, so substituting this into my original equation, minus 1 cubed plus 3 lots of 1 squared minus 1. Because again, we want to find the exact location of this point. So it's going to be minus 1 plus 3 minus 1. So y is going to be equal to what? 1. So point of inflection at 1, 1. So lots of working out. I probably shouldn't have drawn my graph as big as I did. Anyway, so essentially what's saying is that this is the point where it stops going from concave up to concave down. So sketching this thing, so it's up, and like that, and then back down. So it's something like this. Okay, and so that's our function there. And so our stationary points, I should actually try and make it so it's a maximum. So this is at what, 0, minus 1. This is at 2, 3, and this is at 1, 1. Okay, and there we go. So that's our graph of that one. That's our 4 marker. So it's actually quite a bit of work to do that in there. But just do your best with it. You know, it's all about derivatives and second derivatives, so it's nothing that's too hard. It's just a lot of work. Okay. Let's have a look at this one. So, find the integral of this. Now, I know, and that's because I've just recently done this, but I know that the integral of, well, if you have the derivative of something on top of the derivative of the function itself, then it turns into the logarithm function. Okay. So what we need to do in this case is we need to get this thing to be the derivative of the thing on the bottom. So if my function on the bottom is 4 plus x squared, then my derivative is equal to 2x. Now the issue with the function that I've been given to integrate is that I don't have 2x on the top. I've actually got x over 4 plus x. So to do that, what we're going to do is we're going to multiply the function by 1. Now how we've multiplied that by 1 is a little bit, it's a little bit sneaky. What we're going to do is we're going to multiply the top of the function by the number that we need to get it to. So we need to get it to 2x. So I'm going to multiply the top of the function by 2x. I'm going to get 2x over 4 plus x squared dx. And what I'm going to do now is I'm going to also divide the function, or multiply the function, by the reciprocal of that too, so 1 over 2. So what this is effectively doing is I'm multiplying the function by 2 over 2. Which is just 1. So it's still the same size, and it's going to give me the same value, but what it allows me to do is to integrate this with much more ease. So from this point here, now it's just a matter of using your standard integral form. So your standard integral form says that if we have this, so the derivative of the function on top of the function itself, then we get log, or the natural log, of the absolute value of your function plus c. Now it's not going to be negative because we can't have the logarithm of a negative, so it's going to be the positive function of whatever it is. So in this case, it's going to be half of log of the absolute value of 4 plus x squared, so the function that we had, and then plus c on the end. And so there we go. Okay, next, just a simple differentiation. So differentiate e to the 2x, lots of 2x plus 1. So this is a product rule with u and v. So u is equal to e to the 2x, v is equal to 2x plus 1. du dx is equal to e to the 2x, dv dx is equal to. Now, to differentiate this, so d dx of e to the 2x, lots of 2x plus 1. It's going to be v u dash plus u v dash, which is, I believe, one of our differential calculus standard forms. So, in fact, on your formula sheet, it actually says dy dx is equal to u dv, or u v dash, plus v u dash. But it doesn't actually matter which order you put these ones in. I like putting the v first because then that way it actually matches what the quotient rule is, which is v du minus u dv, and that one actually does matter what the order you do it. So putting this in, we get 2x plus 1 times 2e to the 2x plus e to the 2x times 2, which is 2e to the 2x, lots of 2x plus 1, plus 2e to the 2x. And look at that, we've actually got 2e to the 2x in common. So let's take out as a common factor, and we're left with 2x plus 1 plus 1. So in fact, the derivative of this is 2x plus 2, and from here we can, and like this, all these steps are not necessary, this is just extra simplification. If we take a factor of 2 out, we've actually got 2 times 2e to the 2x, lots of x plus 1, and so what we end up with is 4e to the 2x, lots of x plus 1, which looks a much nicer than, say, this line here. Anyway, that's just some extra steps that we can do, just a little bit of extra algebra. And hence find this. Now, well, this is convenient because this actually looks a lot like what we've got here. So in fact, actually simplifying that extra step has become really useful for us to solve this problem. So let's have a look at how we're actually going to approach this. If I have a look at the function that I finished off with when I differentiated it, what I'm saying is my initial function I had up here, when I differentiate that, I get this guy down here, which is 4 more than what I have here. So if I want to integrate this function, so this one here, I'll end up back at this value here. The only problem is I'll have, a fourth of what I originally have. So simply put, x plus 1 e to the 2x dx, this is equal to, well, if this one is 4 more, and it gives me that, then I need a fourth of the function that I started with, okay? Because that 4 is missing. So to basically go from this line here to this line here, I just need a fourth of what I did. And by doing that, it allows me to get this value here. Cool. All right, let's move on to the next one and have a look. Ugh, trig stuff. Gross. Yuck. Can we just skip that one? What do we think? Hate trig stuff. But we'll get into it. Okay. Now, the only one I can't quite remember is sec, but I think from the top of my head, sec, cosec, and cot. So sec, I believe, goes with cos. So what this is actually 1 over cos theta minus cos theta. Okay, so that's what this thing actually means. But what we want to do is we want to go from one side to the other side. So which one do we start off with? Which one do we want to start off with and which one do we want to go to? I actually like the looks of this one better, but I suspect that the other side's going to be a bit easier. So we might go from this side. So sec theta minus cos theta is equal to 1 over cos theta minus cos theta, which is equal to, now, what we're gonna have to do is we're gonna have to have a common denominator. So that's the same as 1 over cos theta minus cos theta, so times by cos squared theta. That's not going to work. What am I doing? I need to get the thing on the top and the bottom the same. So this is the same as cos theta over 1. So, oh, I did it the wrong way around. Just one of those nights, I think. Cos squared theta over cos theta. Okay. And so from here, we get 1 minus cos squared theta over cos theta. Now, there's a really cool little trigonometric identity. So trig identity, alert. And it's actually going to be really useful. And it says that if I have sine squared plus cos squared, that's equal to 1. Or in other words, if I have cos squared theta, that is equal to 1 minus... Sorry, if I want to rearrange this for sine squared theta, that gives me 1 minus cos squared theta, which coincidentally is this thing up here. So what we can do is we can actually replace 1 minus cos squared theta with sine squared theta. Now, if you're not too sure why that is, have a look at the Pythagorean identity. Okay, it's the one that will show you why this is the case. But what we can do now is we can treat this as a sine theta times sine theta over cos theta, which is the same as sine theta over cos theta times sine theta, or other way around, which is the same as sine theta. In fact, actually, I might do it like that so I don't confuse anyone. Which is the same as sine theta times sine theta on cos theta, which is the same as sine theta times, or sine theta, excuse me, times tan theta, like that, which is equal to the right hand side. Okay, I'm just going to have a little bit of a break for a moment and I'll be back and we'll continue on with the next bit. Okay, sorry about that. Well, thanks for waiting, I guess, if you're still watching. But I just need a little bit of a break. My voice is starting to sort of croak a little bit, so must be getting sick. Cough, cough. Hopefully not COVID. And for those of you, if you're watching this in the future, don't know what COVID is, well, God help us all, because YouTube must have taken over the world by then. Kenzo is driving his car along a road while his friend records the velocity of the car, v of t, in kilometers per hour, every minute over a 5-minute period. The table gives the velocity v of t in time t hours as the following. Okay, so the time is every 1/60th of a... Yeah, it must be every 60th of an hour. Okay, anyway. The distance of the distance covered by the car over the 5-minute period is given by this. Use the trapezoidal rule for the velocity of each of the 6 time values to find the approximate distance in kilometers the car has traveled in the 5-minute period. Give your answer correct to 1 decimal place. Wow. Okay, so the trapezoidal rule is a very last integral thing on your formula sheet, and what it says is it looks something like this: from a to b, f of x dx is approximately equal to. So this is in the cases like what we've got here. We can only really do an approximation because we don't know what the exact velocity is. But f of a plus f of b plus 2 lots of f of the first x value plus the second x value up to the x value you need just before we close it off. Okay. Where a and b are x and 0 and x and where a and b are x of 0 and x1 x1. So anyway, substituting these values in. We've got 0 to 5 on 60, and our function is v of t, so from above, and it's going to be dt is approximately equal to, so b minus a, so it's going to be 5 on 60 minus 0 over 2. And it's going to be the function value at a. So my function value at a in this case is this value here. Okay, so that's the value I'm going to get. So it's going to be 60 plus, and the value I finish off at is just 67, plus 2 lots of 55 plus 65 plus 68 plus 70. Okay. Now it should be pretty obvious where those numbers have come from. Okay, so first number, last number, first number, last number, everything in between. Okay. So nothing too tricky there. So what this is going to be equal to, so 50 over 60 over 2 is going to be 5 over 120 times whatever that adds up to. So just pop it into a calculator, I think is the best way to solve something like this. So 5 over 120 times 60 plus 67 plus 2 lots of 55 plus 65 plus 68 plus 70. Close it off. And we get approximately 26.8 kilometers that he's traveled. So when we integrate velocity, it's going to give us the displacement, so the distance that he's traveled. Okay, laptop is spazzing out again. Oh, geez, it's at the end already. God, that was quick. It only took me an hour. Did that seriously only take me an hour and a half? Bloody hell, that was really quick. Oh no, there's a second booklet. That's right, I remember how this exam worked now, and it wasn't ideal. Alright. Okay, back working. Sorry about the spazzing out of that. So yeah, it's part 2 booklet. Okay, so it's really odd, but here we are. So booklet 2. So 58 marks in this one. So oh jeez, it's got like half the bloody test to go. I wonder if it felt like it took no time at all. Anyway, what can you do about it? Hot tea is poured into a cup. The temperature of the tea can be modeled by this thing here, when T is the temperature of the tea in degrees Celsius, T minutes after it's been poured. What is the temperature of the tea 4 minutes after it has been poured? Well, time is equal to 4 in that case, so it's going to be T is equal to 25 plus 70 lots of 1.5 minus 0.4 T, well in this case T, as we said, is 4. So T 25 plus 70, so 1.5 to the power of minus 0.4 to the power of minus 0.4 times 4, and it's about 61 degrees. So it doesn't say how many decimal places that we want, so I'm just going to write 61.6 degrees Celsius. Okay, the next question is, At what rate is the tea cooling 4 minutes after it has been poured? So in other words, we're going to have to differentiate this to find the rate at t is equal to so d what's going to be dt. It's actually funny they use the letter T for the drink tea. Well, it's actually the temperature. Anyway, it's just amusing that T is T. Things like that amuse me too much, I think. Anyway, so at what rate is the tea cooling 4 minutes after it's been poured? So dt is going to be, in this case... I suspect there's an easier way to do this than the way that I'm suspecting. Maybe not. So, constant term will cancel out and disappear, okay? And this will come down the front, and we'll be left with what we normally have. So dt minus 0.4 times 70 lots of 1.5 to the power of 0.4t, negative 0.4t. Sorry about that. Okay, so in other words, I don't really want to work that out. 0.4 times 70, I don't think it's going to be something nice. Oh, it's 28, okay. So minus 28, lots of 1.5 to negative 0.4t. And so that's dt. Cool. How long after the tea has been poured will it take for the temperature to reach 55 degrees Celsius? How long after the tea is poured? So we're going to have to substitute that into this guy here. And so this one, this value is capital T. That looks like an I. So T is equal to 55 degrees Celsius. Then we'll go with... So it's going to be 55 is equal to 25 plus 70 oops 1.5 negative 0.14. So we have to find what t is going to be. Alrighty, so it's going to be a little bit tricky this one, but start off by subtracting both sides by 25, and we're going to get what 30 is equal to 70 1.5 to the negative 0.4t. Okay, so we're going to get 30 on 70 is equal to 1.5 to the negative 0.4t. Okay. I suspect we're going to take logs of 1.5, of base 1.5. So log 1.5 of 30 on 70 is equal to, well, log of 1.5 of 1.5 to negative 0.4t. Now the cool thing about this is that we can use our log law. It says take the thing power on the inside and bring it out the front. Okay, and the cool thing about that is that log 1.5 of 1.5, in other words, 1.5 to the power of what is equal to 1.5, it's just 1.5. And then finally we just need to divide by negative 0.4. So we get what, log 1.5 of 30 on 70 over minus 0.4 is equal to T. So therefore my temperature in this case is going to be equal to... I can do this because my calculator is great. Remember, this calculator is HSC legal, so please take one in with you. Over negative 0.4. We get 5.22 minutes. There we go. Nice and easy. I've got to stop doing that. I've got to stop clicking on things. Okay. Well, the diagram shows a regular decagon, 10-sided shape with all sides equal to and all interior angles equal. The decagon has an O. Like, the perimeter of the shape is 80. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So AB equals 8 centimeters. That's very convenient. I'm going to start off writing that. All right, 80 divide 10, which is equal to 8 centimeters. By considering triangle OAB, calculate the area of the 10-sided shape. Give your answer in square centimeters correct to 1 decimal place. So, if you have a look at this guy, don't want that. If you have a look at this guy, this length here and this length here are going to be the same. Okay, we know that this length here is going to be 8. We know that this angle in here is going to be 360 divided by 10. So it's going to be 36. So theta is equal to 360 divided by 10, which is equal to 36 degrees. Not Celsius this time, like the last question. Don't get confused. Now from here, by considering the triangle, calculate the area of the 10-sided shape. So the only area formula I know that involves an angle and some side lengths is the area formula. So, well, not the area formula, but the trigonometric stuff. The sine, or what is it? Area is equal to half AB sine C. Now, I don't think we actually need that, because I think what we can do is, if I just get rid of that for a moment, we can draw up a right angle triangle here, and that will allow us to find this length here. Once we've done that, which will be the same size as this one here, we can work out what our what the value of the area is going to be using it. Using A is equal to half AB sine C before I forget. So we need some trig on this one, and we know that this angle in here is going to be, so it's going to be equal to 18 degrees. So effectively we have this triangle, it sits like this, with 18 degrees in there, like that, 4 here, and we're trying to find that there. So that's going to be opposite over hypotenuse, which is sine. So sine of 18 degrees is equal to opposite over x. So therefore, x is equal to 4 over sine 18 degrees. So x is equal to, so we'll put this into a calculator, get 4 over sine 18 degrees, which is 1 decimal place, so 12.9 centimeters, I want to say, but I'm not sure because I can't remember centimeters. Yep, centimeters. Cool. Righty, so from here, we know that that length is equal to 12.9 centimeters, and we can work, excuse me. So that's our A and our B value, so A is equal to 12.9, B is equal to 12.9. We know that theta is equal to 36 degrees. What we can do now is we can use A is equal to half times A times B times sine C. Well, that's our C value, I guess you could say. Put it into that. We get half times 12.9 times 12.9 times sine of 36 degrees. And then the total area is going to be equal to 10 times half times 12.9 squared times sine 36. If you're not sure where I got that squared from, it's just because it's 12.9 times 12.9. So let's plug it in. 10 times 12.9 squared times sine of 36 degrees gives us, 978.1 centimeters squared. Okay, that's the end of that question. Alright, next one. Okay, continuous random variable x has the following probability function. Okay, I haven't actually done this at all. No, we haven't done this yet, so I'm going to skip over that and continue on to this one. Alrighty, so we've got a circle is reflected in the x-axis. Sketch the reflected circle showing the coordinates of the center and the radius. So here's our circle here. So let's put it into a form that we're actually good with. So we've got x squared minus 6x plus, and I'll leave a gap there, y squared plus 4y, and I'll leave a gap there, minus 3 is equal to 0. And in fact, I'm actually going to put the 3 onto the other side. You'll see why in a moment. Now, to put a circle into, well, the easiest way to look at a circle is if we have it in the form x minus a squared plus y minus b squared is equal to r squared. So this form comes from the, well, this form here is a circle with radius r and center 0, 0. And this is the more general one, which is a circle with center AB. Okay, so with the center AB, which is like the difference. So if I can turn these guys back into that, that'd be useful. So we're going to do that by completing the square. So the way I do this is I go, well, what's half of 6, which is half of negative 6, which is negative 3. And I'm going to add that back on. And I'm going to square it and add that. So minus 3 squared is 9. So I'm going to add 9 there, and I'm going to add 9 there. And I'll do the same thing for this one. So half of 4 is 2. 2 squared is 4 and 4. So x squared minus 6x plus 9, we can actually now factorize that. And the reason why I put the minus 3 down here is because it actually just becomes x minus 3 all squared. Plus y plus 2, positive 2 squared. And that's going to be equal to 9, 10, 11, 12, 13, 14, 15, 16, which is a nice number for our radius. So sketch the reflected circle showing the coordinates. So, oh, come on, work for me, baby. Let's go. Yeah, good. Okay, so to reflect circle with, or in, I should say, in the showing the coordinates in the center area. So in the x-axis, so that is anything that is above the x-axis will go below, and anything below the x-axis will go above. And I'm going to actually draw this up properly. So bang, bang, there, go across there. It'd be so much easier if we had these in exams, that's for sure. Okay, so put him there. Sorry about that. Okay, I'm going to move that so it's somewhat in the center, like this. Okay, it's going to look something like that. Turn him back off. Off, thank you. Good. Okay, and for the sake of the argument, we're going to go across by 2's and up by 2's. So minus 6, minus 4, minus 2, 2, 4, 6, 2, 4, 6, minus 2, minus 4, minus 6. Got my x values, got my y values here. Okay, so let's sketch the original function. So, sorry, the original circle, not a function, it's a relation. So my radius is at 3 and at negative 2. Okay, and we've got a radius of 4. So it's r squared, so 16. So 16 is what's the square root? So square root that, you get 4. Okay, so if we've got a radius of 4, Then it's going to go up 1, 2, 3, 4. It's going to go across 1, 2, 3, 4. It's going to go down 1, 2, 3, 4. It's going to go across 1, 2, 3, 4 like that. Okay. So all my x values are going to essentially swap their spots, and the y values are going to stay where they are. So my center is going to go from being at 3, -2, and it's going to move to 3, +2. So it's going to move up here. Okay, so that's center, and then we just go the same way. So 1, 2, 3, 4. Actually, well, that's convenient. So the difference is 4. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So you get the circle. That looks horribly bad, but we'll give you the marks in the HSC. So I think the last thing was to put on the coordinates. So sketch the reflected circle showing the coordinates and of the center and the radius. So radius, and the center is going to be 3, 2. There we go. Beautiful, beautiful circle. Looks like a lemon. Beautiful circle. Okay. 25. I'm hoping we're getting to the end soon because I'm starting to get a bit tired. Anyway. A landscape gardener wants to build a garden bed in the shape of a rectangle attached to a quarter circle. Let x be the x and y be the dimensions of the rectangle in meters as shown in the diagram. Show that the perimeter is equal to 2x plus 72 on x. Okay. The garden bed is required to have an area of 36 meters squared and have a perimeter which is as small as possible. Let p meters be the perimeter of the garden bed. Okay, so if I know that the garden bed... So the garden bed is this bit in here. Okay, so this is the garden bed here. Okay, so it's just that rectangle bit. So we know that that garden bit is equal to... 36 centimeters meters squared. Okay. And we know that the x value... Do we actually know anything about the x value? We don't. But we can write the area in terms of y. So the area, let's start off with the area. Okay. So it's 36 is equal to x times y, so xy. So we can rewrite the area in terms of y as y is equal to 36 over x. And so this is an expression that will give us the area based on our x value. So that means that this line up here can also be written as 36 over x. So now that when I go to find the perimeter, I can add up all the different bits. So x here, now I don't need the x bit here because it's not part of the perimeter. The perimeter is just the outside. But I do have this bit here and this bit here, which are both the same. So that's also 36 on x. I've got this bit here, which is the same as this bit here, which is, in this case, my x value. And I've got this bit along here. So to get that bit, oh, we don't actually need the circle just yet. So we're just getting a little bit ahead of myself. So I only need this stuff on this side here. So let's go, well, the perimeter. So we go perimeter is equal to, so it's going to be x plus 2y, where y is equal to 36 on x. And we just add the two together. So we'll all of them together. So it's going to be x plus 2 times 36 on x. So the perimeter is going to be equal to I guess it does. It is including this one because if you're just doing the perimeter of just the garden bit, it's going to be including that bit, I guess. So we will include that one. That's just where that 2x from the front is going to come from. Plus, well, 2 times 36 is 72 over x like that, and so that's the perimeter. as required. Okay, so down here's the next one. Don't know what happened to that page, but it's alright. Find the smallest possible perimeter of the garden bed, showing why this is the minimum perimeter. So what we're actually going to do in this case is we're going to do some calculus, okay? So my perimeter is equal to, so the equation that gives me the perimeter, regardless, in terms of one variable, x, as we've discussed, is 2x plus 72 on x. God. 72 on x. Now this can be rewritten as p is equal to 2x plus 72x to the negative 1. So rewriting that over x as x to the negative 1. Now from here, we're actually going to differentiate the perimeter in respect to x. And for it to be its minimum value, we need to find a turning point. So we'll get to that in a moment. So this thing here, so it's going to be 2 plus, or in fact minus 72x to the negative 2. Okay, or dp dx is equal to 2 minus 72 on x squared. Okay, now, excuse me. Now, for our, actually this is going to work really nicely. I actually really like this one. Sorry. For our minimum or maximum, we want to find when that's equal to 0. So in other words, we want to solve this equation here. So minus 2 is equal to minus 72 on x squared, which is the same as, I've got heaps of space, so no need to worry there. So minus 2x squared is equal to minus 72. Okay, divide both sides by negative 2 and you get 36. So x is going to be equal to plus or minus 6. Now we only want positive because we can't have a negative area. Okay, so that's going to be the value that gives us the most of that thing. Now to check to make sure it's a minimum, to check for the minimum. Now this might be overkill in the HSC, but we do need to show that it is a minimum, not a maximum amount. We're going to do the second derivative. So dp dx, so I think it's to be d squared p over dx squared, and that's going to be equal to, so if I look at the equation back up here, it's going to be positive 72, so it's 144x to the negative 3. And at x is equal to 6, we're going to get 144 on 6 cubed. So that means that this thing here is going to be equal to, so 144 on 6. Two and 3. So because that's greater than 0, it is therefore a minimum point, and thus x is equal to 6 is the minimum perimeter value for x. Okay. Find the smallest possible perimeter. So now we just got to substitute that in. So I'm going to do this up here. So perimeter at x is equal to 6. So my formula for my perimeter is p is equal to 2x plus 72 on x. So p is equal to 2 times 6 plus 72 on 6. So therefore my perimeter is going to be equal to 12 plus 72 on 6, 24, whatever it is, meters, I think. It's just meters because it is a perimeter. It's a length, not an area. Okay, I haven't done finance yet, so I'm just going to leave that one for now. I'll come back to it at some other point in the future. Which means that I'm going to avoid that one, and I'm going to avoid that one too. And out of sheer principle, I'm going to not do question 27, because it is such a rubbish question that, well, we haven't done stats yet in my class, so we're not going to do that just yet. But also because it's just like there's so much information here, and like this massive thing here is just so that you know, because I have done this question previously, but it's just so that you know that the median is 22. Like that's the only reason you need this whole bloody graph, is so you know the median is 22. So we're going to ignore that. It can go. And we're going to go to 28, because 28 sounds a bit more fun. It's statistics. All right, I'll have a crack at this one. I'm not too, like, as I said earlier on, I'm not super comfortable with my statistics just yet. I'm a teacher. I should probably know this stuff, but, like, my class that I'm currently teaching at the moment, my first senior class, we haven't quite got there yet, so, but we'll have a crack. Looking at the first question, can't actually do that because I don't actually know it, so, it's been good. It's been good. Okay, this one I could probably do. So, we've got y is equal to c natural log of x. Okay, show that the equation of the tangent to that at x is equal to p, where p is greater than 0, is this. So, to create a tangent, we need two things. We need, number one is a point. Number two is a gradient. And what this will allow us to do is substitute it into the point gradient formula, which is that one there. So let's start off by finding out what our gradient is. So what we're going to start off by doing is working out what our derivative is, substitute our point in, and that should give us the gradient at that point. So the derivative of, so if I write this up here, so y is equal to c natural log of x, then our derivative is going to be c on x in that case. Now, we want the gradient at point when x is equal to p. Okay, so when x is equal to p is what point we want. So we're going to substitute that in, and therefore our gradient is equal to c over p. Okay, and if you have a look, that's actually what we need for that value there. So our gradient, now a point, so at x is equal to p, our y value is going to be c natural log of p. So p, c log of p. So this question itself is not actually too hard. And I'm going to stop here and mention this. It's not actually too hard because it's just applying the things that you should have learnt in class. But just with letters instead of numbers. Like, there's no difference. You just substitute the letter wherever you see the number like you normally would. Alright. So from here, we can substitute it into the point gradient form. So our y minus y1 is equal to m lots of x minus x1. So by doing that, we get y minus our y1 value, which is c natural log of p. And that's equal to c over p of x minus c over p of our x value, which is p. So that will cancel out with that. And what we'll end up with is y is equal to c over px minus c plus c log of p, like that. Okay, so that's just putting the c log of p on the other side as well. So just what we needed. So we're happy with that one. Okay, find the value of c such that the tangent from part A has a gradient of 1 and passes through the origin. So find the value of c that has a tangent from part A and has a gradient of 1 and passes through the origin. Whew. It's a bit of a toughie, this one. Find the value of c such that the tangent from part A has a gradient of 1. Okay, so we'll start off with this bit first. So part A is a gradient of 1. So that is, we want our derivative to be equal to 1. Okay. And passes through the origin. So, well, okay, so the origin, so point that we're going to be working with is 0, 0. So there's x is equal to 0 and y is equal to 0. Now this is useful because when we go for our gradient, well, we can't actually work that out because we can't substitute 0 into our gradient. So, find the value of c such that the tangent from part A has a gradient of 1 and passes through the origin. Sorry. Find the value of c such that the tangent from part A has a gradient of 1 and passes through the origin. Find the value of c such that the tangent from part A has a gradient of 1 and passes through the origin. It's a gradient of 1. So we need to work out what a p-value is. I think it's going to be E, just from thinking about this, using a little bit of logic and applying a little bit of logic. Find the value with c such that the tangent from part A has a gradient of 1 and passes through the origin. The tangent from part A has a gradient of 1 and passes through the origin. So, geez, this is really stumping me. So if it passes through the origin, it must satisfy 0, 0. So if I substitute 0, 0 into that, it should work. My p-value must be equal to E, which makes my c-value must be equal to... So, well, if I get rid of this bit. So this is my thinking, and I don't know if this is right or not. But we're going to sub it into the tangent. So in other words, we're going to get 0 is equal to c over p, lots of 0, minus c plus c log of p. Okay, in other words, 0 is going to be equal to minus c plus c log of p. Now, the only way for this to be true So this can only be true if log p, c log of p is equal to c, i.e. if log of p is equal to 1. Now the only case when p is equal to 1, or log of p is equal to 1, so this is log e of p is equal to 1 when p is equal to e. Okay. So if p is equal to e, this changes our equation to y is equal to c on e, x minus e plus minus c log e. Now, for gradient to be equal to 1, c over e must be equal to 1, okay? So i.e. c must be equal to e, okay? So therefore, c must be equal to e. Like, that's the only way for that to work. So that's kind of what I suspected to begin with, but it's just a really sort of long way around doing it. Very, very disappointed that you retracted your message, Mr. Wise, but can't always have things our own ways, I guess. It's actually really convenient because this is like exactly what we're doing at the moment. Very, very convenient. Yeah, that's just a really tough question. I'd be interested to see what band they've stuck that at. I'll have to have a look at some point, I guess. Anyway, let's move on to the next one. What do we got? Ugh. That's okay, buddy. It's just mucking around. Not a worry. Alright, the diagram shows two parabolas. Y is equal to 4x minus x squared and y is equal to ax squared. Ugh, more general stuff. Where a is greater than 0, the two parabolas intersect at the origin, O and at a. Alright, show that the x-coordinate of a is 4 over a plus 1. So essentially what we're going to be doing is showing that these things intersect. So, in this case, we just want to show these things intersect. So in other words, when is this thing equal to this thing? Now they're both in terms of y, so we can just write them as ax squared is equal to 4x minus x squared, like that. Solving this, okay, so we get ax squared plus x squared minus 4x is equal to 0. Okay. Show the x-coordinate of a. So I think, and this is I think, we can divide through by x to get ax plus x minus 4 is equal to 0. We'll make this ax plus x is equal to 4. And then from here, take a factor of x out, get a plus 1 is equal to 4, and then divide that by a plus 1. So we get x is equal to 4 over a plus 1. Well, that's bloody convenient. Alright, okay, continues on the next page. Find the value of a such the shaded area is 16 on 3. Oh, well, that's going to be a bit rough. The shaded area is 16 on 3. Well, we know what the x value is now. So this is starting to get to your pretty hairy questions, this one. So we want the integral in this case. We want the integral from 0, I think it was, from 0. Yep, so it's going to be from this point here to this point here. And it's going to be this function minus that function, okay? And we're going to be finding the value for when that's the case. Right, so from 0 to 4 on a plus 1 of 4x minus x squared. Sorry, it's going to be a little bit jumping back and forth just for the moment. Minus, was it ax squared? Dx? Yep, cool. Okay. So, let's integrate this. Integrating this, nothing too tricky here. We get 4x squared on 2, so it's going to be 2x squared. Minus x cubed on 3. Minus ax cubed on 3. And it's going to be from 0 to 4 on a plus 1. Okay, so we're going to get two lots of 4 on a plus 1. Well, the 0 is going to cancel everything out, so it's not going to be an issue. 4 on a plus 1 cubed over 3 minus a lots of 4 on a plus 1 cubed on 3. Okay, and it's going to be minus 0, minus 0, minus 0. Okay, so we don't need that bit. It's going to be 8 on a plus 1 minus 4, 16, 64. So that guy is going to go on the bottom. That minus 64a on 3 lots of a plus 1 cubed. Wow, okay. And we want this to be equal to 16 on 3 is equal to that. This is so gross. What the hell am I meant to do with this? Oh, well, okay, I can rewrite this one as a plus 1. It's equal to that. Well, if I guess I could subtract, get 16 on 3 minus 8 on a plus 1 is equal to this gross monstrosity. I don't think this is going to be right, but what else can you do? So 16a plus 1 minus 8, 16, 24. And they give me lots of bloody space, but far out. This is nuts. Okay, so 16a plus 16 minus 24 times 3a plus 1 cubed is equal to 64 plus 64a times... Oh my god, this is actually disgusting. Oh, what the hell? This can't be right. This cannot be right. Am I missing something? So it's from 4 on a plus 1. From 0 to 4 on a plus 1. Oh, I don't think I am. I think this is just really, really gross. Okay, so we've got 16a minus 8. 3 lots of... that. If I expand this side out, what do we get? Like, this is just such disgusting numbers. If this works out, I'm actually going to cry a bit and then I'm going to go to bed. But, 192 a plus 192 plus 192 a squared. Outside first, outside, inside, plus 192. Is that right? A. No, the last one should have an A as well. Oh, which is a really nice quadratic, actually. Alrighty. 16a minus 8. 3a cubed plus 9a squared plus 9a plus 3. So if I take the 192 out, I'm actually left with a squared plus 2a plus 1, which is so nice. It's just this left-hand side is so disgusting. This can't be right. Far out. 1632 48. 16 by 9. It'd be what? 160 take 16 is 144. Plus 144a plus 48. 8, 16, 24, so minus 24a cubed minus 72a squared minus 72a plus minus 24. Well, if I can somehow get some a squareds plus 2a's plus 1s out of this, actually, this is going to simplify really nicely. Huh. Anyway, let's do some simplifying. We've got 48a to the power of 4. Plus 120a cubed. Plus... yeah, that's something gross. So that's 72 a squared. Oh no, this isn't right. This is not right. I don't know why I'm continuing with this, to be honest. I think actually this line up above might... So if I take a squared out, if I take 48a squared out, how many times does 48 go in 144? That would be the question. Actually, actually, I want to go this. Oh, that's heaps better, actually. Completely wrong order, but really, really quite good, actually. It's 96 would be better. Hmm. 72 and 144 are very, very closely related. Perhaps too closely related, actually, although... If I go 48a to the power of 4, and what's double of 48? That's 96. So can I get 96 out of the a cubes? I get 120. That's not useful. Have I done this expansion right? Oh, it's actually driving me mental. Okay, I'm going to stop there because that's actually driving me spare. Stop. The population of mice on an isolated island can be modified by the function this, where t is the time in weeks, and from 0 to t to 52, the population of mice reaches a maximum of 35,000 when t is equal to 13. So that's our t is equal to 13 there. And a minimum of 5,000 when 39. The graph of mt is shown. What are the values of a and b? Okay, so t is your period. So this guy is your period here. So that's how far... No, that's how quickly it's going. This guy here is how far it's moved up. So halfway between the 2 points. So 3,000 on 2, which is equal to 1,500. So I should probably write that in the space. So a is equal to 30,000, or I'll do it the proper way. Show all my working out. Uh, 15b. So what did 1 get multiplied by to shift it up? Yeah, so it should be like what? 1,500. Yeah, there you go. So b is equal to 20,000. On the same island, population of cats can be modeled by this function. Consider the graph of mt and the graph of ct. Find the values of between 0 and t, which the populations are increasing. Which both populations are increasing. Right. So, haven't done differentiation of tree yet, but that shouldn't be an issue. Derivative comes out. So, c dash of t is going to be... It's going to be at sine 80 lots of derivative of inside comes out. So just that of sine okay, and well, further populations are increasing for when both populations are increasing. So when is this guy greater than 0 for increase? So C of t is going to be equal to, well, it's essentially when so times both sides, divide both sides, you get sine pi on 26 t minus 10 is greater than 26 on 80 pi. Inverse sine, you're left with pi on 26. T minus 10 is greater than inverse sine of 26 on 80 pi. So t minus 10 is going to be greater than 6 on pi. 26 on... This can't be right either. I think there is a... There's a link between me saying this isn't right and the later I get into this exam. It's only one value too, like when both the populations are increasing, so it's just when they're both greater than 0? So if that's greater than 0 and that's greater than 0, can you say anything about that? Actually, I wonder if that makes it easier if you solve it simultaneously. So I know if both things are equal to 0, then you can say each thing is equal to each other. But if they're both greater than 0, what can you say about that? For a 2 marker though, isn't it? It's a lot of work. Oh no, it's a 3 marker. Just ignore it and move on. Bloody hell, this is way too late to be doing a maths exam. Okay, and that's the end of the paper. We'll fancy that. Well, from what I've learned is that I myself need to be doing a bit more in this regards too, because, and like it should speak like absolute, you know, absolute, what's the word, like volumes for how much you should be doing. Like after a 4-year maths degree at university and teaching the course, like there's still so much that I can't just do off the top of my head. And look, a lot of this stuff I actually do learn as we progress, in the sense that I need to keep on top of it, otherwise I do forget. But if we have a look at the solutions, there's actually a couple I wanted to look at. So if we download the marking guidelines, this will help. So okay, so looking back at 31, in fact, actually what I'll do is Okay, sorry about that. So what I was going to do is I was going to have a quick look at this and have a look in relation to what we actually did. So, for example, like if we look at part B, what they've got, like that doesn't feel like it actually matches the question that we were given. So the question was, here's another function. Consider the graph MT and the graph of CT. Oh, where's my mouse? Like, we don't have the graph of CT. And... oh, well, they've drawn it. Okay, so they've just essentially drawn the thing and said, okay, let's have a look at it and see when it decreases and when it increases. I guess that would probably be easier than actually trying to solve it simultaneously. Overthinking things for stuff that's not necessarily needing the overthinking. Now, the one question I do want to look at was this bloody thing. Right, so I will zoom in. So you start off with this function and you make it equal to 16 on 3, which is not an issue. So that's what we did. We integrated it and got... oh no, so they actually factorized it first and then integrated it to get the same thing. Okay, well that doesn't make much of a difference because that's what I would have gotten anyway. To some extent. So 32... yeah, okay, so substitute it in, you get that. Substitute this one in and you get that times that. Okay, that's fine. So you get that equal to 16. Okay. So 96. Oh, and you... okay. So I was on the right track, but just not anywhere close in regard. So if we have a look back at this one, like... sorry, just give me a moment. Come on, Mousy, where are you? There you are. Okay, so if I go back to my one, so essentially by having all of this stuff here, if I made this, well, hang on. Oh, because I got the A+1 on top. So, am I missing an A somewhere? Oh, because they factorize it. So factorizing it makes it so much easier. And I said that at the start too, I'm pretty sure. I said, well, that looks really convenient. But we'll leave it split up. But I shouldn't have left it split up. So annoying. It would have been so much easier if I didn't do that. Anyway. So if we go back and have a look at this one. Here, it's some of the other solutions. So... I can't even remember what these questions were. Okay, so this was this one, yeah. So C had to be equal to Eve in that regards. So that one was fine. So I ended up getting that one in the end. It's just took my bloody brain a bit to bloody... oh, that was the first part of that one. So yeah, that was the formula. That was fine. No issues there. Not doing statistics yet, so ignoring those. And the money ones as well, I'm not doing just yet. When x is equal to 6 and 24 meters, yep, awesome, so that one was fine. And that was finding the actual perimeter in terms of that. There's our circle there, which had, so that was the original and that was the new one, so that was fine, there's no issues with that one. I didn't do that one because I wasn't super confident with it, I don't think. Anyway, this one here was the... they used the sine rule for this one. So this was the 36 by 72, 72. That's actually interesting. So I split it up and found what R was by doing trigonometry, so finding 18 degrees, which gave me a number that was like double that. What? Oh, because I forgot to put the half in. Duh. Silly. Silly. So it should have been 5 times that, so that's why I got double. Oh, well. Got the 5.22 minutes for that one, which was the T one. So just substitute the value into the first bit, then get the 5.9. Oh, we had to actually find out what the T value was. So I just substituted it in. So what I needed to do then was actually put the value into that and get what the derivative would have been, which I don't recall actually doing. Anyway. That was the trapezoidal rule. That was a very, very easy one that I feel like I got wrong because I forgot to put it over the 2. Oh, I need to check that one now. The issue with these is that so many different screens. Everything's everywhere. What question was it? 20. So a little bit further up. In fact, I'll actually skip back over so you guys can see what I'm doing. So is question 20 in this one? No, question 20. Oh, this one here. Yeah, so 560 on 2. Don't know what I did wrong there, actually. B minus 8 on 2 of the values. 5 on 60 minus 0 on 2. They've just got a random 5 sitting on the bottom there, which I don't actually understand why that's there at all. Because I suspect I put the wrong thing in. I think it's meant to be over 2n, where n is the amount of points you've got, so up to 5 in this case. Whoopsies. Oh well. So that's this one here. So I'm thinking that 5 there was to determine how many like trapezia you have. I don't know why you divide by 5 though. Anyway. Oh, because there's a 5th of each of the thing. Yeah. Duh. Anyway, okay. This one here was pretty good. This trig one. I quite enjoyed that one. Well, there you go. So if you got up to that point there and didn't know what to do with this line, then you actually got 1 mark. So that's pretty cool. The integral for this one. So that was the one where we had the 4th of the thing, which was quite cool. I really like that one because it was set up with this one here. And question 17 was the log of this thing here. So that was a good one too. Nice and easy, straightforward one. Yeah, a function looks something like that. Pretty cool. Point of inflection, top, bottom, and thing over there. Have a look at the criteria, like 4 markers, lots of stuff there. Now, I suspect that this one... Oh, for God's sakes. I don't even know where this came from. Up here. Okay. I suspect now... So there's my function there. It's this one over here. Yes, part C. Now, they've done the sine rule. And I'm not... whoopsie daisies. I'm not 100% sure how you can apply the... How you can apply the sine rule to this thing here. So, if we... So, just get rid of this stuff on here. So get rid of that, get rid of that, get rid of that. Okay. So the question was to find what. So I suspect, sorry, just, yeah, okay, there we go. So the question was to find the group. So find the bearing of Mrs. Brown's group from, bloody hell, I do not know why I just didn't do the sign rule. Like, no, hang on. I know why I didn't do the sign rule. So, what they reckon is, so, sine of A over 9. So, this angle in here over this, sine of that angle over there, is equal to sine of this angle over this. Okay, which would make sense why you'd have to find that. So, A is equal to that. And so, this value up here is equal to 69. And then they say it's 180, so this, minus 69 minus 35. And I'm guessing that 35 is up here. So if you have your line here, okay, so like, so I guess if you've got it like this, okay, then if this is 35 degrees in here, okay, then this angle in here is 35 degrees there. Now we know that the total of this angle in here, so the total is, oh well, okay, so you use trig to work out the total is going to be 69 degrees. Okay, so this whole thing's going to be 69 degrees. Now all of this is going to be 180, so it's going to be 180 plus 35 to get to this point here, and take away 69 to get back, or 60, whatever it was, 69 to get back there, which gives you 146 degrees. So a little bit of thinking involved in that one there, which yeah, just didn't come to me for some reason. Did not come for me. Okay, so there it is there. So yeah, you can see where the 35 is. Okay, and then if that whole thing is 69, then that's 180. So 180 plus 35, take away 69, get you back there. Yeah, okay. Sample answer for that one. No issue. That was a probability one, I think. Yeah, 10 over 39, 13 over 18, 1 over 8. Yeah, no issues there. This one here, the tan one, yeah, it's equal to 1. That's right. Really odd way for you to get 1. Now, this is the one I wasn't too sure about. So the n value in this case is 226. So you start off by saying your difference is 6 and you... right. So if we look over onto our formula sheet, I'm going to zoom in on this one. So here's our formula sheet here. And up on the first page, you've got these 4 formulas here. Now this sequence here, this sum here must tell you the number of terms in a sequence, I suspect. So A and D. So if A is 6 and sorry, A is 4 and D is 6, and we know the number, oh yeah, of course. So the number we want to get to is 1,354. So you substitute that part into the first bit, and you do 4 plus n minus 1 times 6. So you subtract 4, divide by 6 to get that, and then you take 1 away. So you know that the number is 226, and then you substitute it into this formula here. So 226 over the first plus the last, and so the sum of that must be equal to this value here. Cool. Okay, so that's not too bad. I genuinely forget what this one was even asking about. This one was the... I'll get it back up. Come on, buddy. You can do it for me. Oh, this was the tank one. Okay, so the tank one was quite easy. So... yes, here we go. So here's the drawing. Tank A, tank B. So if you go down 29, and if you go back across, you get the thingo, and then we worked out using both simultaneous equations. Can we actually just work? Thank you. I might just unplug you if you're making so much noise. Yeah. Sorry about that. Okay. So yeah, so that value is not too bad. Now, part C, B, and so that was part C, B, and A. Okay, so that's not too bad. Now the multi-choice. So let's have a look at our multiple choice, and we'll see how we went. So this is the criteria. I will just say the answers as we go through them. So I'll switch over to the main screen so you guys can see. Okay, so the first one was D, happy with that. Second one was B, happy with that. Third one was A, awesome. This one here was B. This one here was C. Okay, I know there's one I wasn't too sure about. This one I was happy with this. And this one here was A, so excellent there. Now, this one here, I put A and that was correct. But again, I'm just not 100% sure about this last bit here because I suspect that if you draw your gradient along here, okay, and, you know, like that's quite a low point down here, but the tangent's quite steep. So, I'm not too sure, you know, when this would swap around. Anyway, question 9 was actually C. Okay, not too sure. So as I said, I'm not 100% sure about statistics, but I suspected it might have been D because I was sure these were the quarters. You know, quarter 1, quarter 2, quarter 3, quarter 4. Like these were your quarters. But if you think about it, like, you know, you've actually got more data points out here, so it's not necessarily the quarters. Those are the quarters. Well, actually, this one, yeah, just yeah, I'm not sure. And the last one, this one is D. So yeah, we got that with the up, down, up, down. Well, 9 out of 10 in the multiple choice didn't really translate over to the short answer, but the rest of the exam, I should say. Some pretty tough ones in there, and if you don't know all of your stuff, you're going to be pretty stuffed come the actual exam. So yeah, just something to keep in mind in the future. Alright guys, well that's the end of the first stream. I hope you got something out of it, even if it was just to, you know, watch me sort of flounder a bit with a lot of those questions. 2 hours and 48 is what we're at now, so not too sure in what regards we would be in relation to the actual exam. You know, if I actually sat down and did a big revision session before it, and, you know, was confident on everything, I'd be really keen to start over again. So with that being said too, I'll be doing revision sort of stuff throughout the holidays, leading up to the HSC, and after the HSC I'll well, not after the HSC, but, you know, this term, next term. So this term probably not as many. Next term we'll be ramping it up. The holidays I'll be absolutely pumping it. So we'll do some really big revision lessons, and in fact we'll be doing that actually in class. So actually in a classroom. So that'd be good. So it'd be like, you know, you were a part of my class, which I think's always a cool little feature. And yeah, so it's just a matter of then going up to the HSC, which I will be trying my best to do. So my main focus, I think, will be standard and advanced. Extension 1, you know, like I'm quite good at, but not super confident with. And then extension 2, like I can do some extension 2, as my extension 2 class knows, but a lot of the time it's usually a little bit of a working together, because I'm not 100% confident on the extension 2 stuff, but, you know, that's just the way it is. Anyway, I hope everything was awesome for you guys, and I hope you enjoyed the music. I hope you enjoyed you know, watching a little bit of maths, and you know, I'll see you guys in the next one. So take care, and see you then.